All right. Okay, I'm Katie.
I'm Lisa.
And we are reviewing different methods to modify peanut proteins to reduce their allergenicity. So just a background of what is currently going on with, or a background of our papers is peanut allergy is one of the most prevalent food allergies worldwide. So it's estimated that 0.6% of American children and about 0.5% of kids globally are allergic to peanuts. But avoidance is always going to be the best method for these patients who are allergic to peanuts. But peanuts are involved in many food products, so there's potential for residue on processing equipment or in the food. We are looking at the RH1 protein, but Lisa's paper also covers the RH2 and 3. But this is the most abundant allergen in the peanut kernel. It is present as a trimer with each monomer having a molecular weight of 63.5 kilodalton. It is a viscilin, and it is mediated by hydrophobic interactions. So it's easy to degrade, but it has a very strong allergenicity. But it can be recognized by 90% of patients' serum, so this is why it is used in studies.
So here's just a little bit background on the structure of the molecules involved in allergenicity. On the left, you can see the antigens on the top and the antibodies on the bottom, and the key parts of these molecules are the epitope on the antigen and then the recognition sites on the antibody, and those are the key binding things going on when you have allergenicity. So everything involved in these research papers is about what goes on at that reaction or maybe changing how it fits. And when you look at the image on the right, it shows that one antigen can have multiple epitopes. So even though you might be able to change one structure, it might still bind in other ways. And then you can have multiple antibodies for those epitopes. So even if you change the structure one way, you might end up making it able to be bound to a different antibody. So there's just a big challenge in allergenicity just because of the variability in both of these molecules involved. So there's some general strategies for reducing allergenicity, adding on to the challenges with these structures. The photo at the bottom shows two different kinds of epitopes. So you can have linear epitopes where it's a continuous strand of protein that binds to the antibody, and then you can have a conformational or a discontinuous epitope, which is where the protein has different amino acids that are binding, but they're not connected in a continuous way on that strand, so you can have folding and all of that. So that's just one of the other challenges with proteins, is that you can form new conformational or linear epitopes with changing in structure. So one of the first methods is changing the secondary and tertiary structure, and that's most commonly through thermal treatments. That can be useful for maybe conformational epitopes, but maybe not other ways. Maillard-induced glycation, which adds a carbohydrate onto the epitope, that might be useful for different kinds of epitopes. Hydrolysis, which is the breaking of epitopes, and then fermentation, where lots of different things go on and the protein is digested. In the papers we're talking about, the first paper that Katie's going over is about thermal treatments, so it'll cover the first strategy, and then the paper I'll be talking about is about enzymatic hydrolysis, which is the second strategy.
So like Lisa said, we are talking about thermal processing, methods on the structure and allergenicity of the peanut protein RH1, and the influence of enzymatic hydrolysis on, and this one's on 3 different proteins. So just an overview is thermal processing studied the effect of thermal processing methods to decrease the allergenicity of the RH1 epitope. And they tested boiled and fried peanuts as compared to the crude peanut. So they measured surface hydrophobicity, structural changes, and IgE binding, and the allergenicity was reduced in both treatments, the boiled and fried treatments, but at varying levels. And then the enzymatic hydrolysis study used 2 different enzymes to break down allergic proteins in roasted peanuts, and they focused on 3 different peanut allergens, the RH1, 2, and 3. And this one measured the degree of hydrolysis, fragment sizes, and allergenicity to the patient antibodies, and again, there was a reduction seen in allergenicity. So the first study, again, is on the thermal processing methods. Kind of the justification for this is This was a study done in China, and in China there is a very low peanut allergy prevalence. It's believed that the thermal processing methods such as roasting, boiling, and frying are the reason. So back to, in the background, I mentioned that there was a 0.6 or 0.5% of children in the world and in the U.S. are allergic to peanuts, but in China it's reported as almost none. And they didn't give it, couldn't find a number for that, but almost none indicates it's much less than 0.5%. It has been found that the Maillard reaction can increase allergenicity by exposing conformational epitopes on the surface which were previously hidden, and that would be through conformational changes. But a separate study shows that boiling decreases allergenicity by causing aggregation and changes in secondary structure. But all the other studies that they looked at ignored the effect of the food matrix in these thermal processes and artificially induced heat treatments. So in this study, it's different because the peanut as a whole peanut underwent the thermal processes instead of just the protein itself. So their objective was to clarify the effect of heat treatment methods on the allergenicity of the RAH1 protein in peanuts. And their hypothesis was that boiling and frying peanuts will create a conformational change in the secondary structure of the RAH1 protein, therefore reducing total allergenicity. So they took 3 packages of 300 grams peanuts each for each method, so for the crude, boiled, and fried peanuts. The peanuts were either boiled at 100 degrees Celsius for 20 minutes or fried at 120 degrees for 20 minutes. And then all the peanuts were frozen with nitrogen, ground, defatted. The protein was solubilized, centrifuged, and then freeze-dried and stored until they were going to use it. The human involvement was that serum from 7 patients who had previously been tested positive for peanut allergy, or they used serum from 7 patients, and then their immunoactivity was tested as a pool sample. So to to purify the RAH1 protein, they used anion exchange chromatography, and they found, so the top, my labels got a little mixed up, but the top one should be crude, then boiled, and then fried. They noticed that for the fried peanuts there was no change in allergenicity, but this figure is questionable because if you look, so again it's the top one and the bottom one, they're pretty much identical, so we're kind of wondering if they just used the same graph there. And that's supported by, there were a lot of errors in this paper. But in the boiled peanuts, so in the middle one, there was a larger separation in the 2 fractions, which indicates that there was a conformational change because of an increase in net negative charge on the surface of the protein. And even though these are in different scales, you can see that the fraction 1 and fraction 2 has increased compared to the crude treatment. Then to determine the binding efficiency to the IgE, they used Western blot. So over here we have the fried peanuts, the boiled peanuts, the crude peanuts, the positive control and the negative control. Or no, the positive control and negative control. So you can compare them and see that the crude peanut still has regained in lane 3, it still has regained quite a bit of IgE binding. But then as you move over to the boiled peanuts in lane 4, there is decreased binding. And then in lane 5, the fried peanuts does have decreased binding, but it is still a significant amount remained. To quantify the allergenicity, they used ELISA. Both peanuts had a reduced allergenicity, but to different levels. The boiled peanuts in the middle, again my labels are all screwed up, but the boiled peanuts in the middle have the biggest reduction in allergenicity. So we estimated it to be about 21%. They didn't provide a number, but they did provide a number for the fried peanuts, and that one decreased in allergenicity by 9.4% compared to the control. Then they measured surface hydrophobicity with the fluorescent probe method. Both showed a change in hydrophobicity on the surface, but the boiled peanuts only had a slight increase in surface hydrophobicity, whereas the fried peanuts had a 13-fold increase, largely or likely due to the heating medium. Then they measured changes in secondary structure. So the alpha helix, which is the first one, that decreased in both, but it decreased the most in the fried peanuts. The second column is the beta sheet content, and that increased in both. And if you notice, there was also a ratio flip in the amount of beta sheet to alpha helix. And then the content of beta turns kind of remained the same, but the content of irregular coils increased only in the fried peanuts. So tertiary structure, they measured tryptophan, the amount of tryptophan on the surface. So for the boiled peanuts, they found that there was a decreased wavelength, which indicates that the polarity around tryptophan decreased, or the tryptophan residues gathered inside of the protein structure. And then for the fried peanuts, there was an increase in wavelength, which suggests that there was an increase of tryptophan on the surface, likely due to structural change, and this is supported by the hydrophobicity index. Their major findings were that the immunoreactivity of the RIH1 protein in boiled peanuts was the lowest, so it was a reduction of 21%. And the secondary and tertiary structural changes occurred in both treatments. They also found that hydrophobic interactions can induce, break, or hide conformational epitopes due to structural changes, but many of their conclusions were not supported. And this kind of goes into that. So first thing is, it would have been nice for them to include a roasting treatment, since that was one of their justifications for the study, was that roasting, boiling, and frying peanuts was a cause for the reduced allergenicity in China. And some big issues we had with this were not all of the graphs in the series were on the same scale, and we thought maybe even one of them was copied and reused. There are also many typos within the graphs and within the paper, sometimes making the results unclear. And the organization of the data was very unorganized. Things weren't presented in a logical order, and it didn't follow the method section that they had written up. They should have included a graph of percent reduction in allergenicity, and they could have looked at the individual sera to assess the individual reactivity of the serums, because this was, everyone's different, and this was only a pooled test. And then again, many of their conclusions were not supported, so they weren't supported by science, so it's hard to trust any of this really as fact.
Yeah, so our second paper was called The Influence of Enzymatic Hydrolysis on the Allergenicity of Roasted Peanut Protein Extract, and this one was a little bit better of a paper than the first one we had picked. So it's from a bigger journal, the International Archives of Allergy and Immunology. So the justification for this one is, once again, trying to find some solutions for the challenges with peanut allergies, especially since other modification methods have sometimes worked, sometimes not. Enzymatic hydrolysis is commonly used in industry for making hydrolysates, and then using alkalies and flavorzyme for these research was an idea they had, since it was promising in chickpeas and lentils for reducing allergenicity. So the objective of their study was to investigate the individual and the sequential action of alkylase and flavorzyme in the IgE binding properties of the soluble protein fraction of roasted peanut, using sera from patients with a clinical allergy to peanuts. For their design, they used sera from 5 patients with peanut allergies, which might sound small, but the normal range is anywhere from 5 to 10 people. Their peanut preparation involved using roasted peanut, so keep in mind there is probably some Maillard reaction going on before using it. They milled it, defatted it, and air dried it, and then they extracted the peanut flour, centrifuged, dialyzed, and then freeze dried it. For their enzymatic hydrolysis method, they did a sequential treatment of both of the enzymes and then 2 individual treatments. The sequential treatment was the total time of 480 minutes with 180 minutes of the alkylase first and then 300 minutes of the flavorzyme next. For the second treatment, they just did alkylase alone, and then the third treatment was just flavorzyme alone. But one odd thing was that they used 2 different levels of the alkylase enzyme. So in the sequential one, they did 0.4 AU, and AU is just the measure of the alkylase activity. But in the 180 alkylase alone, they did 0.2. For their analysis methods, they looked at the degree of hydrolysis. They did protein profiling with SDS page and 2-dimensional. And then for immunoreactivity, they used ELISA and immunoblots, which they looked at anti-ERA H1, 2, and 3 antigens. And then I just wanted to point out that alkylase is an endoprotease and flavorzyme is an exoprotease. So part of choosing those is that they picked 2 enzymes with majority different functions. Flavorzyme can also be an endoprotease, but a large majority of its function is as exoprotease. So here's what their hydrolysis curve looked like. To create the curve, they collected samples throughout the reaction, inactivated the enzymes, and then measured the degree of hydrolysis by measuring the number of free amine groups. One part to look at is that there was a really rapid initial hydrolysis for all 3 of the enzymes from 0 to 30 minutes. Another thing I noticed was that the rate of the sequential treatment was kind of really uneven. I don't know if that would be normal or not, but that was just something interesting I noticed. And then the final degree of hydrolysis they achieved for each of them was for alkylase alone was 17%, flavorzyme alone was 29%, and then the sequential treatment was 69%, which is higher than the 2 combined because they used a higher alkylase in that one, which is kind of an odd thing that they did. So one criticism I have for this is that they did not provide any justification for these time lengths. I would have expected them to use the same amount of time for all 3, but they did like smaller segments and longer segments and then combine them for the whole treatment, and they just didn't provide justification for that. They were copying a method from a previous paper that was looking at the chickpeas and lentils, but that one didn't have any justification either. So. And then another criticism I have is their difference in the alkylase concentration between 0.4 and 0.2. They also didn't acknowledge that or provide any justification for that, but just keep that in mind as we look at all their results. So their SDS page results looked like this. The first column in all 3 is just the roasted protein, and the bands for that fell between 10 to 63 kilodalton. From just looking at the alkylase treatment, at the very beginning of the sequential one is alkylase and then alkylase alone, they looked pretty similar, even though the concentrations were different. Looking at the flavorzyme one, throughout the whole time, it kind of had small effects throughout, or effects in certain bands and not others. And then comparing the flavorzyme in the flavorzyme alone compared to how it did in the sequential treatment, it reduced it a lot more in the sequential treatment. And that would make sense considering that the alkylase is already doing the endoprotease work and creating lots of short fragments for the flavorzyme to have more ends to react at. But one question I had on this was that if you look at the x-axis, which is in minutes of the SDS page, that's only goes up to 300, whereas the whole reaction went on for 480 minutes. So the degree of hydrolysis goes all the way to 480, and if we're showing the SDS page just to 300, it's only covering this red box of time, and they didn't give any justification for not showing it, what it was at the very end. And then my other one is that the first column after the roasted protein one is 0.25, and that's in minutes, so that's a 15-second time point. And they didn't give any justification for why they did a 15-second time point, especially considering that the next time point is 30 minutes and goes even higher than that from 180 minutes and higher. So it's a really short time frame. They didn't explain why they did it. And yeah, but it did show a pretty big reduction from the start time to the 15 seconds, but yeah. So then the Western blot is down below. To do the Western blot, they used a pool of the 5-patient serum to see their IgE binding efficiency. The first one, if you can look at, is the sequential treatment. It overall reduced it a lot, compared to the roasted protein column. If you compare the alkylase to the sequential one, there was a difference in that 15-second time point if you look at the first one, but overall the reduction is still high to the right of that. And then one interesting thing to point out is on the Flavorzyme one, there's a band right around 22 kilodalton that kind of remained throughout and didn't decrease. And so they later took that and isolated it to find out what it was too. But one criticism I have for this is just it's really poor contrast for the Western blot. If you can make it any brighter or anything like that, it was just hard to see. So not only did they do Western blot with the pool of the serum, but they did look at individual patients. So they chose these 3 patients, 1, 2, and 4, and did it with just their individual sera. So none of the sera recognized really any of the proteins after the sequential hydrolysis. But keep in mind, this is only at the 300-minute mark. It's not even at the 480-minute mark, but I would presume it would also be kind of empty at the 480-minute mark. After the Flavorzyme treatment, there were still multiple bands recognized for all 3 patients. And then my criticism is that they discussed that it was there wasn't any sera recognized after the end of sequential hydrolysis, but this again doesn't show the 480-minute endpoint, it just shows the 300-minute endpoint. So for 2-dimensional analysis, this is just to explore what was left in that Flavorzyme one when it was that 22 kilodalton band, and that was still there after 5 hours of hydrolysis. So the spots that are visible in the Flavorzyme middle one is right around 15 kilodalton and 3 to 9 pH. And then if you look at Western blot, the ones that were still there were right around 22 kilodalton and 5 to 7 pH. So they later took that and tried to identify it with MALDI-TOF, and then they connected it to ARA-H3 peanut antigen. So they were finding that this enzymatic method maybe isn't great for reducing that antigen. But keep in mind, they only looked at ARA-H1, 2, and 3 throughout this, so there's way more than just those in peanuts. So it might be useful for those 3, but maybe not the rest. And then for ELISA, this shows on the top the optical density, so how intense the reactions are with the antigens, and then at the bottom they can show it next to the degree of hydrolysis so that we can say how early in the reaction we were getting a reduction in allergenicity. For this, they used the serum pool of the 5 patients, and then the cutoff point that they chose, right, this line across there, is the level that they would say no peanuts, or that it's not allergenic anymore. So they were seeing some significant decreases in allergenicity for both the sequential treatment and the alkylase treatment. One interesting thing to point out is on Flavorzyme, the reactivity went back up partway through, so that could be going back to the structural challenges that we talked about at the beginning. It could be creating more or exposing more areas of allergenicity than before. So the IgE was reduced 100% with only 11 to 16% degree of hydrolysis using alkylase alone, which is really useful or beneficial considering that higher degrees of hydrolysis make just very poor sensory or functional properties. And then they took immunoblots, so they wanted to see the reactivity with just ARA-H1, 2, and 3 alone, so they couldn't do that with the patient sera since it's a mixture of antibodies. And so in this case, they used chicken antibodies. And so they use it to measure before and after treatment how it reacted with these 3. And then overall, there was a decrease in recognition of all 3 of these units after the sequential treatment. It was basically disappeared. And so the major findings are that Flavorzyme alone after 300 minutes reached a higher degree of hydrolysis than alkylase alone. But the SDS page fragment lengths did show differences. The immunoblot and ELISA showed reductions in allergenicity, which is promising. So no sera recognized the roasted peanut proteins after 30 minutes of sequential hydrolysis. And that finding was supported by the previous chickpea studies that they were basing their methods after. And then that was all based on the patient's sera and confirmed with Western blot. And then an increase in allergenicity occurred after flavorzyme treatment, which is what I had just pointed out. And individual 2D blots were identified with MALDI-TOF as subunits of area H3, so they were able to find out what was still there after all the reaction time. And specific area H1, 2, and 3 experience revealed that sequential hydrolysis decreased antigen levels even within the first minute of reaction. Just a few more, or summary of the comments and criticisms and other questions I have after reading the study is that there just wasn't enough justification in their methods for everything they did. So the difference in reaction times, differences in enzyme usage, and then why they did a sequential treatment instead of maybe both at the same time. Some results that I had criticisms for was that it didn't show the 480-minute results on their STS page in Western blot. They didn't show the results from their MALDI-TOF analysis to show that it was the area H3. They said it and said the data wasn't shown, but it'd be nice to just include that too. They had some typos, some missing units on graphs, and then just some incomplete graphs. But this paper was written by a research group in Spain, so maybe there's language barriers. But and then one thing we kind of found out at the end is that their serum pool might not have had explicit area H1 or area H3 antibodies. So maybe the pool of people that they tested didn't have that comprehensive of an antibody profile. So all their results are just dependent on how variable their patient's sera is, and maybe they're based on how their results looked, it looked like it might not have had those 2 antibodies. And in general, it's important to consider the sensory, nutritional, and functional aspects of too high of a percent degree of hydrolysis, just due to really short protein fragments. And further studies are needed about the insoluble fraction of roasted protein, considering that this was only about the soluble fraction, as well as sensory and nutritional studies.
Skip that. The summary, skip it.
Okay. I'll skip the summary of studies, and that's all.
Okay, great. Good. Thank you. All right. Questions? Lucy?
For the first paper on thermal treatment, did they have any explanation, I guess, of why the secondary structure flipped in terms of the beta sheets to alpha helices?
They didn't, but if I were to guess, it's because the beta sheet is a higher thermal stability. So it would be more likely for it to change to beta sheet, I guess, as opposed to alpha helix. It would go away from alpha helix because it's less thermally stable. That's what I thought, but they didn't mention anything.
Yeah, yes, that is correct. If you remember from lecture, we talk about when you heat, alpha helixes oftentimes are lost and instead beta sheet form. So usually people look at alpha helix to beta sheet ratio, and it's an indication of denaturation of that ratio. So if they don't do the SC and if they don't look at tertiary structure, if they just look at secondary structure, by just looking at alpha helix to beta sheet ratio, they can say that, okay, the protein is denatured or got under thermal treatment.
Yeah.
Good, Beth?
So I guess the enzymatic reactions, do you know what temperatures they were run at and if temperatures were used to inactivate? And then following that up, would that, based on what you learned from the first paper, possibly influence the results of the second paper?
I think they did it close to room temperature, 50. They use 50 C, so it's warm, a little bit warmer, but.
They did denature?
But yeah,
Is that what
is
the
there any potential denaturation that could have influenced those results?
Yeah, because they want to inactivate the enzyme, did they?
I don't think it mentioned denaturation,
Yeah.
but I think through hydrolysis that would obviously change the protein.
No, but did they inactivate the enzyme by thermal treatment so that might cause further denaturation?
To do the degree of hydrolysis analysis, or just in general?
Hydrolyze, usually you inactivate your enzyme at the end of the hydrolysis.
Oh,
They
okay.
do that.
I don't remember reading that.
No. They should
I
have.
could follow up. Yeah, I don't know.
But yeah, oh, weird that they didn't. Any other questions?
Going back to the secondary structure, so you said that they saw more random coils for frying the peanuts. Do you know why, or give an explanation?
Again, they didn't explain, they just stated it.
What do you think, Katie?
Yeah, that's what I was.
So actually, that's a good question, because that was a question of mine as well. You've noticed a lot of changes happening with frying versus boiling in the structure. What do you think is that?
I would guess it would have to do with the hydrophobicity. There was no mention of the number of hydrophobic amino acids versus hydrophilic. I would guess there's more hydrophobic and they're naturally present on the inside, based on what I remember from lecture, but we didn't go into the structure of the protein.
So if you think about the temperature treatment of boiling versus frying, which one would be more adverse? Temperature.
The higher temperature? The frying has a higher temperature.
So yeah, so I think the exposure of higher temperature would have resulted more in changes that they've seen. They did not explain that, but this would be the obvious kind of explanation. Yeah, they see a lot of changes in secondary and tertiary structure, and that is because of the higher temperature. So Katie, go back. Is there any other questions from Rachel?
I had just one, and it's kind of a general question. Do you know how many antibodies are like correlated with peanut allergy as like a whole? Because you said that there's only 3.
The first slide I had of just our intro at the very beginning, there was that picture of just a bunch of different ones. So there's, I think, at least 9 identified, but sometimes certain ones have subunits or maybe different structures too.
Yeah, so there could be a lot of different antibodies, but I think what Rachel, when you do is they specifically selected 3 proteins and looked for specific antibodies for these 3 proteins.
Okay.
So they looked at the 3 most allergenic proteins and they got the purified antibody for each one of them because the sera is not purified. The sera would have all sorts of antibodies to all sorts of epitopes and different proteins.
Yeah, I was talking about the antigens, sorry, not the antibodies.
Okay.
Yeah.
But yeah, you're right. So there are probably 9 antigens, but the antibodies could be infinite number of antibodies because each protein might have several epitopes too.
So it's not more question but more discussion and comment. So they said it's a sampling period was 15 seconds. Is it because they were too picky to not say it's time 0? Then after doing all the samples, I go back to the first sample and I consider it more like a 15
I wrote
seconds.
that down. It could be a control sample.
It's a
They added
control
the enzyme
sample
and stopped
and
the reaction
stopped the
right
reaction
away.
and something like that.
Yeah.
So
I just realized that.
technically people, that is one of the
Everybody's asking my question.
Even though there was a pretty big difference between the
brain
roasted
is,
protein and that point.
that
Yeah.
was one of the thing, and the second thing was the 300 minutes. Is it considered because they wanted to analyze everything at the same time point? Because I saw 2 other graphs were stopping at 300, and only one of them was going at 480 to have a uniform to hand. Was it considered to be done everything at 300 minutes? Do you think that would be the reason they decided to do all this?
I mean, they were consistent with the 300-minute
Yeah.
limit on all their gel-related
Yeah.
things. So maybe they just couldn't fit everything on there, and they just picked that and were consistent. But they still didn't provide justification for it. And that if you're looking at the sequential one, that means you're not getting the full flavorzyme treatment. You're getting shorter than the flavorzyme. You're getting a shorter flavorzyme treatment in that one than you are in the full flavorzyme treatment alone. So you're still not getting a great comparison of them. Not to mention that alkylase was different. So there's a lot.
They were not clear in specifying that, but I guess that could be why they stopped at 300 just to do the. But they didn't justify. If you want to stop at 300, make sure that all of your experiments are at 300. And the other thing is they did say that after 300, 300 you don't see any more bending and no more reaction. So they did say at 480 they didn't. So it's kind of common when you don't see results, you can say this is what you see in data not shown.
Yeah.
Yeah. So they could clarify this a little bit more. But speaking about time, I don't know if you mentioned this, I don't think you did, but do you think the time that they selected is feasible for industrial applications?
Not really. Some of the ones that are really long are just like hours and hours, so no. But at the end, when it showed, they did get a really high reduction after just 16% degree of hydrolysis. So those might be feasible.
Yeah.
Going somewhere along their route might be feasible. But once again, this isn't reducing all of the antigens. It's just some of them, but it's, yeah.
Good. I really have one more last thing. Go to the figure of the anion exchange. I think this would be valuable for people in class too. I mean, a lot of this papers are not that great, but at least we're learning and discussing, not linking what we learned in class. Okay. Do you really see a shift here? Because this has been expanded. So this one is coming sooner, is what I'm seeing. This starts here at 60. This is starting at 40.
So this one starts before 100 and this one starts after 100.
A little bit, but this is the one that shifted. This is the one that came earlier.
But I think this one also came a little, I think
Yeah,
they spread it.
yeah, but okay, so this has shifted a lot and this has shifted a little and that caused. So that doesn't mean that this is necessarily as much higher net negative charge than this one. This could have potentially lost charge. So that's why it eluted earlier. Does that make sense to you? Yeah? So the way they explained it is that this one shifted too much, but really both of them shifted. And this is the one that shifted almost 20 minutes back. Yeah. So I think this peak, something happened here too in terms of charge, and this one probably gained a little bit more charge. But the way that they have this scale is really messed things up. You don't want to publish like that. Just, you get to the wrong conclusions and you confuse the people that are reading your paper as well. All right, well, very good, thank you. Are you ready? Okay, good. My computer is thinking. If you want to take any proteins, more training courses. Where are you? Okay, there you are. Okay. What? You don't want to do this? No. Oh, okay. Did it come? Yeah. Okay. We can use that one.
Okay.
Oh, one comment. Obviously, there is no group. So for teamwork and contribution, just give her a full mark for working courageously on her own. So.
What? I'm going to talk about the dielectric barrier discharge co-plasma treatment of peanut protein isolate. And first, the peanut is one of the most important oilseed legumes, and most peanuts are used for extraction of edible oil. And after extraction of the edible oil, you get the byproduct, which is the defat peanut flour. You get 47% to
55% of protein and with low anti-nutritional factors. The advantage of the peanut protein is it has excellent amino acid profile and a captivating aroma and white color and cholesterol-free. But the disadvantage is it compared to soy protein, it has poor functionality properties. That is why we want to modify the peanut protein isolate. And here's the nutrient composition of the peanuts, defatted peanut flour, and peanut protein isolate. So after you extract the oil from the peanuts, you get the DPF, and the protein content is around 45 to 55. And after you extract the protein from the DPF, you get the PPI, which is around 90 to 95% of protein. So three major fractions of the peanut protein is arakin, con-arakin 1, and con-arakin 2. It makes up nearly 75% of peanut total proteins. And the arakin is the most abundant and different from con-arakin in having only 1/3 as much sulfur and in containing less basic nitrogen. And the arakin denature around 90 degrees, con-arakin denature at 80 degrees. And the isoelectric point is about 5. So first of all, what is the plasma? Neutral plasma such as lightning and polar lights is everybody knows. And plasma is regarded as the fourth state of matter. So you have first solid, liquid, and then you have gas. So when a significant amount of energy is applied to the gas through mechanisms such as electric field, and you got electrons that can escape from the atoms and molecules, not only allow the ions move more freely, but also produce more and more electrons and ions via collision. And eventually you get higher number of the electrons or ions change in the electric property of the gas, which becomes ionized gas. So simplify, the plasma consists of positive ions, electrons, and neutral particles. So what is the cold plasma? Plasma can be classified in many different ways. This is just one of the classification based on the relative temperature between electrons, ions, and neutrons. So cold plasma is, what does that mean? It means that the electron temperature is much higher than the ions and neutrons in the plasma, which give the overall plasma around 40 to 50 Celsius. And you can actually use hand to touch the plasma. So there are two ways to produce the cold plasma. One way is under the low pressure, you have the special instrument, you can produce the plasma. And another way, like nowadays, we can produce the cold plasma at atmospheric pressure. So the instrument related to atmospheric pressure cold plasma is DBD and corona. And the low pressure plasma is float discharge. So in this case, in this study, we use DBD as in cold plasma to treat the peanut protein. So this is an overview of cold plasma application, and there are different kind of areas which can use cold plasma. So focus on the food science. Most research doing the peptide dissipation, microbial inactivation, and enzyme inactivation. Finally, we got the property modification. We can use cold plasma to modify starch, protein, but not lipid, because plasma contains the active reactive oxygen species, which may cause the food to lipids to oxidize, and you don't want to oxidize the oil too much. And this paper is published 2018 from Chen's research group. In total, they published 8 papers related to cold plasma treated on protein, and this is one of the papers they published. So the justification of this paper is improvement in its functionalities of peanut protein isolate may be crucial to increase its application in food industry. The objective of this study is to evaluate the effect of cold plasma treatment on peanut protein isolate. So the experimental design, they got the commercial defatted pea flour, and then they extract the peanut protein isolate, use alkaline extraction and isoelectric precipitation around 4.5, and then there's freeze dryer there, PPI, and then they disperse the PPI powder to make the solution. They inject 10 milliliter of PPI solution subject to settled voltage for 1, 2, and 3, 4 minutes to see the time effect on the peanut protein isolate. So after the treatment, they divide it into two parts. The first part, they can directly test the surface hydrophobicity, particle diameter, and total exposed free sulfur hydrate content, and solubility, and water holding capacity. The result of the solution was freeze dried to obtain PPI powder, and they got the protein profile by SDS page, protein denaturation by DSA, and protein secondary structure by FTIR. So here is an illustration of how the instrument looks like and how it works. So they have the plasma generators, and they settle the voltage and ampere they want to use, and they put the 10 milliliter PPI solution under the plasma. Here is the electron, and this is a dielectric barrier which make plasma can be generated under the atmosphere pressure. So they put the sample there, and on the right there is actually picture when you use the cold plasma to treat the protein. So here's the result for the structure. First of all, they get the SDS page. All the sample was mixed with 2% of SDS and 5% of reducing agent, and in comparison to the untreated PPI, treated PPI shows no difference in the electric for their SDS page. But they stated that the SDS page result indicate the CP treatment failed to show any effect on the non-covalent interaction or SDS bond, but it's actually wrong because they added SDS and also reducing agent, which could break down all the non-covalent and also SDS bonds. So they obviously they cannot say any polymerization under this reducing under reducing conditions. So here's the result for FTIR. They look at the amine region for the secondary structures. The alpha helix, as you can see, the increase of the treatment time, the alpha helix decrease. The trend of the beta sheet, random coil, or beta term is actually unclear, but however, they state they have a trend, but I don't believe that. So, but the ratio of alpha helix to beta sheet was decreased, which can indicate a certain degree of denaturation. So we can say that the more time you use cold plasma to treat the protein, even it's 40 to 50 Celsius, the reactive species actually denature the protein. So here's the DSA result. I'm sorry for this result because the trend is also unclear, and I will show the stats. So they have 96 for the enthalpy and the 90 for the enthalpy, and they are in the same group, but there was the significant difference between 96 to 92. So I don't believe this result. So moving on to functionality. So there is one solubility.
Are magnets to bad figures.
So here's the solubility. They measure all the pH and also the solubility. The reason they measure the pH is from previous research related to cold plasma. All the protein or whatever you decrease the pH. So they measure the pH and also use the buffer too. Although they use the buffer, but there was a little bit decrease on the pH in this case, and because the cold plasma will form the nitrous acids and nitric acid and also hydrogen peroxide. And the solubility of PPI solution first increase from 0 to 2 minutes and then maintain the same. So here's the result for the water holding capacity and low field MMR result. So water holding capacity result showed that the 0 to 2 minutes, the water holding capacity did improve by the cold plasma, but after 2 to 4 minutes, it actually decreased. But overall, you can see the values that the treatment versus untreatment, you get higher values of water holding capacity or the treated sample compared to untreated one. And the NMR results show that the T21 peak is actually, they measure the gel under the NMR. So the T21 peak means that the water interact with the protein matrix in the gel system. So the only valuable peak is T21. So you can see that with time 0 to 2, it actually increased the T21 peak areas, and after 2 minutes, it actually decreased the T21. It quite matched to the water holding capacity result, that it improved the water holding in the gel system. So here is the emulsion stability result. They use different methods compared to we studied in this class. They use TurboScan stability index, which means that if you have a really stable emulsion over time, it won't change the transmission signal intensity. But if you actually see the oil separate from the water, the intensity will change. So overall, you get TSC value very high, means less stable, and very low means more stable. So after treatment by the cold plasma, you can see all the values is decreased, so it's more stable, and the 2 minutes get the most lower value, so you get the most functionality in this time, 2 minutes cold plasma treatment. So conclusion from this paper, we can conclude that the protein solubility, emulsion stability, and water holding capacity of gel was found to be improved. Unfolding of the protein structure was reviewed by FTIR, and cold plasma treatment might be used to improve the functionality of peanut protein and broaden the application of peanut protein in food industry. So some critiques: they need to adjust the pH before any structure and functionality test, because they want to have the comparable data, and then they need to redo the stats analysis, because all the stats in this paper is wrong, and provide the concentration of the protein solution in a normal way, because they use kilograms per grams. I don't know why they use this way. And they should redo the SDS gel under rundown reducing condition to see if there is any polymerization. And they need to link functionality to the structure changes. And it's unnecessary to separate the solution into two parts, because actually this the idea of separation is they can measure under in the solution, but actually they adjust the concentration of the solution. So I think the better way is to freeze dry anyway and then dissolve in whatever concentration they want. So it's meaningless to do that. Okay. Here's questions.
Okay, any questions for Ben? Rachel?
How do you think that freeze drying would have an influence on some of the tests that were freeze dried versus not freeze dried as far as structure?
I think there must be an effect if you do not freeze dryer and you directly test the solution, because the freeze dryer might have an impact on the protein structure, so it's not consistent if you separate into two parts. And that's a good point.
That's a very good point.
Yeah.
Yeah, but definitely when we're comparing, we're trying to link structure to function, they have to be treated the same way. Because although freeze drying is mild, but we are freezing, we are producing ice crystals, and when you are drying, you are removing these ice crystals, so you are making some changes. Yeah, good. Thank you.
What would be some potential applications of this research?
Application about this research?
Yeah.
It actually, because they are just in total, the paper related to cold plasma to protein functionality in total, I think is around 20 papers, something like that. So this paper actually really new. It's published in 2018. It gives us an idea that it could be you can use the cold plasma to at least improve the emulsion and also water holding capacity, but there's not much study during this area, so we need to more studies toward this area to understand the mechanism behind the cold plasma and also what we can use to modify the functionality.
And whether that modification
Yeah.
of functionality leads to a true application.
Yeah.
Well, follow up on that question. From your reading or from whatever knowledge, do you think cold plasma in general is feasible in industry? At present, I don't think so for protein functionality. But isn't it being
In activation,
used? Isn't it being
Yeah,
used
I think-
in terms of cost, feasibility? I think it's being used for,
yeah.
to kill
So,
microbes.
Actually, for this, sorry.
We're going backwards.
So, in the industry, they use DBD. The reason is that the low pressure one,
What's DBD again?
dielectric barrier discharge. So actually,
I got it. No, I don't know what that is.
so at first they discovered that under low pressure, because there are less collision between electrons and ions, so you do not hate, you actually hate the electrons, not the ions, like not the gas particle. So the gas in overall you don't get the higher temperature because you have low pressure. So the first they generate the glow discharge to generate the cold plasma, and then nowadays the engineers produce the DBD, which is they add the like barrier between two electrons, and then they reduce the intensity. So actually at atmosphere pressure they can produce the cold plasma. So in the previous they cannot produce under the atmospheric. What George has in their lab is low pressure one, so they need expensive pump system. So in industry now they use DBD, so they haven't used this now, the low pressure one.
So potentially can be feasible.
Yeah, potentially for the, especially for the inactivation of the enzyme and bacterial inactivation.
Okay, any other questions?
Following up your question, I think I remember someone, like they were using a similar method and they complain about like they need to keep the distance of the two
Electrodes the same?
Yeah, very like
Thin?
small.
Yeah.
And that's one reason of why it's hard to be applied to the industry, because like the less the distance is,
But-
the less
Yeah,
efficient.
but actually this picture, they produce this one. So which can directly, you have the like this one, and this is the area, and they can whatever the distance you can put your sample. So now they can use in industry, whatever.
Change the distance.
Yeah, you can change the distance whatever you want. So it's more applicable. Use this one. This one.
Very passionate about cold plasma. Yeah, good. Thank you so much.
Okay, go ahead. You have a lot of criticisms for this paper, so like what journal was it from?
It's from. Oh, okay. I actually marked the impact factors. Just want to criticize this journal. It's from bioprocessing engineering, I think. For bioprocessing.
Where do you have that?
For bioprocessing technology is 2.998 nowadays.
It's really high.
And did they explain their statistical methods at all? If you could double check to be like, they didn't.
Actually, there are a lot of like cold plasma papers related to like protein functionality, the quality.
The statistical methods, did they write about that in their methods section? And if they did, was it just the wrong method they used in order to get the wrong stats? Or did they just not explain what they did?
Oh, they just, I don't get
Did
it.
they put statistics in? Did they explain the statistics?
Yeah, no, they didn't explain it. They just put the significant difference. But actually, they are in the same column, like A, B, C.
No, but then in their method, they didn't have a section on statistical analysis?
No,
Okay.
no statistical analysis. Sorry, that's fine.
Okay then. Thank you. Okay, so either I give you 5 minutes now or we don't get 5 minutes. If I give you 5 minutes, that means I'll keep you 5 minutes longer.
No, but
What? What's that? No break?
that's my vote.
But you said if we asked enough questions, you're okay with cutting out.
That's true.
Okay. So do you want a break or do you want me to continue?
I don't want to stay.
Water.
That's what I've heard.
All right,
Drink
so-
some water.
All right, I'll give you 2 minutes, 2 minutes. And I will stop at 3:45. I will cut it short. Oh.
Sorry.
Since we're missing 3 people, stuff. Did you get 2 extra?
I did.
Oh, then these were links then. We got yours. Extra. That's okay. All right. So I was just reminded that I never gave the +5 for attendance. So not sure if you want it still. You can have it. Do you want it? Well, yeah.
So, okay, so today we're giving the +5 for attendance. Whoever is in the room, is anybody missing? No. Can you write it on my participation sheet, and you're going to give this to me today, right? Good. You had a question, please?
Yeah, would you be able to put our points up when the final exam?
Yes, yes. As soon as I grade the final, I'll put everything up. I still have to finalize the presentation, so I was waiting for today too. So I'll put up grades before the final. So, but in all seriousness, are you all good with, was it on the 11th at 8 on Saturday?
Yeah.
Or do you want to move it? Or just be done with it? Saturday at 8?
Maybe like 9.
I'm good with 9, 11. Yes. The only thing is, if you need extra time, I really have to leave by 11:30.
Oh, let's do 8:30.
No, wait, it was 8, right?
It was 8:30.
It's an 8.
Is it really? No.
What's
I
that?
wrote it on the wrong time.
Is it 8 or 8:30? Do you want it 8:30?
Yeah.
30 minutes of sleep.
What's that?
I'll take 30 minutes of extra sleep. Sure.
Yeah.
I mean, you don't need more than 2.5 hours. I mean, 2 hours you should be able to be done, but I'd like to give extra time if needed. So 8:30, I think we should be fine. I need to leave by 11:30 sharp, so we should be fine. That's 3 hours.
What room is that in?
Huh?
What room is it in? Here?
I'm hoping there's no other final that starts at 10 in the same room.
I don't think they do that.
You don't think they do that?
I don't think so.
Okay.
There's no class like after us.
Yeah.
We get kicked out, it's not my fault.
Okay. Yes.
Is there like practice final thing?
No. Yeah. It's so hard to put final exam questions, but you're welcome to ask me questions up until the day of the final. So, yeah.
How many questions is it?
Double the amount of a regular test. Your first test. The second test, I think, even the second test. You had like 5 questions in total? Yeah, it would be about double. Okay, so we were talking about hydrolysis the other time and talking about how we control degree of hydrolysis and the importance of degree of hydrolysis. And the fact that depending on many conditions, the outcomes could be different. So depending on the type of enzyme, the protein, denaturation, here it's a denatured protein and non-denatured protein. With the same enzyme, you get a completely different profile. The conditions, whether it's temperature or pH, pH is very important, ionic strength is very important because it impacts the charges on the protein and how the enzyme can get to particular binding sites. So that will lead to different peptides generation. And with different peptides generated, you get different functionalities, either improvement or not the opposite. So either functionality can be enhanced or decreased. So controlling these conditions are key for the production of hydrolysates. So what we hope for is improvement of functionality. So in general and theoretically, when you break down the protein, you end up with smaller peptides, and smaller peptides have more solubility than larger proteins. And that is not just because the peptides are smaller in size, but also because when you break down a peptide, you are freeing ionizable groups. So you're freeing free amines and carboxyl groups that can react with water. And when we have higher charge, often you have higher thermal stability. That means you resistance to polymerization upon heating, for example, because of the presence of charge and repulsion. And interaction with water versus interaction with protein and peptide proteins or peptide interactions. Depending on the types of peptides released and the size of the peptides released, sometimes a little bit of exoproteases can break down the protein in a way that will make it more pro-gelation, and it's still large protein, not very small peptides. Small peptides will not get you better gelation. And then often when you break down some of that protein, you change the surface activity. So sometimes you enhance the balance between hydrophilic and hydrophobic on the surface. So sometimes you get improved emulsification properties or foaming properties. But there is not one remedy for all, so there is not one enzyme and one condition that will get you improvement of all of the functionalities at some point. It's targeted modification. So often you really want to test different enzyme conditions, different protein denaturation state in order to get to a desired enhancement in functionality. So it is really very tedious thing. It's not like something that you can do with one experiment and figure out the conditions that you need to enhance functionality. So I'm going to give you an example that we did in our lab, a former student of mine. We worked on a product that is very unique. Have you ever heard of delactosed whey?
What do you mean delactosed? Like
Just remove the lactose from whey? Yeah. Then you end up, with the lactose, which is your product, and then you end up with another byproduct that is delactosed whey. Basically, it has all the components, but less concentration of lactose, but it still has about 24% protein. And a little bit of lactose and minerals, obviously. So it is mostly used as animal feed. It doesn't have really much of a food application. And it's high in minerals, but it can be demineralized by reverse osmosis or electrodialysis or ion exchange to concentrate it a little bit more. But the bottom line, it's a very low value product, and it's a lot of it out there. So one time the Midwest Dairy Association put out a call for proposals to find high value applications or to make this product a high value product. It was like, okay, we have protein, what can we do with it? So what we did is we submitted a proposal at the time, and it got funded, and a project was developed, and a grad student looked at ways to amplify the functionality of the protein present. That means we only have 24% protein, but can we make it more functional? Even though it's low protein content, can we make it more functional that we can use it in applications? So we looked at enzymatic modification. We thought, okay, if we do a moderate and targeted enzymatic modification, this of the delactose whey, we can amplify its functionality and therefore add the value. So we wanted to have moderate to limited hydrolysis to enhance functional property. We wanted to limit the degree of hydrolysis so that you don't produce bitter peptides. But then how do we start? We have a wide range of enzymes, like hundreds of enzymes we can choose from. We have multiple conditions that we can combine and put together and try. So we can have either a huge experiment to run or try something different that would reduce the number of experiments we do but still get us an outcome. So have you heard of response surface methodology? Yes, in hopefully the statistics class that you take. So response surface methodology, it allows you to select certain conditions and then run your experiments and get a prediction equation, a polynomial equation that is a prediction equation for the conditions that results in the optimum or the best functionality or the highest functionality. So Y is your functional property, whether you're looking at solubility or emulsification capacity. And then usually you have 2 or 3 factors, sometimes 4 factors, that you would be plotting to determine your equation. And you can only have this plot for two factors, but you can have different slices of plots. I'll show you in a minute, where you can look at all of the factors at different time points or slices of combinations of factors. But the beauty of it is if you say you have 4 independent variables, you're looking at pH, temperature, time, enzyme to substrate ratio, okay? And 1 enzyme, but 4 different factors. And then you have 3 levels within each factor. You have 3 time points, 3 different pHs, 3 different enzyme levels, and 3 different temperatures. So if you want to run a full factorial design, that's 81 different hydrolyses that you're going to need. That is huge. You will never graduate. That's a lot of work. But with response surface methodology, you can you run specific designs and gives you a randomized combination of factors, and usually it's somewhere between 24 to 28 different experiments. So instead of 81, it would be 24, 28, depending on the design you choose under RSM. And then you would run those experiments and do the mathematical analysis to produce the prediction equation. The prediction equation gives you the optimum temperature, the optimum pH, the optimum time, and enzyme to substrate ratio that will give you the highest enhancement in functionality. So this is the actual, this is a sample of the RSM plots that my student generated for degree of hydrolysis and for emulsification capacity. Just an example, and looking at pH versus temperature, or enzyme to substrate ratio versus temperature, or time versus temperature. So you can get any different combinations to make your plots, to see the highest emulsification capacity, under what conditions you get the highest emulsification capacity, and then equations are generated. So after running all of these different plots and getting the polynomial equations, my student, what he worked with is 2 enzymes. So he did alkylase and looked at 4 different variables, and also did propane and looked at 4 different variables. So what we did is we looked at degree of hydrolysis, obviously, emulsification capacity, which is grams of oils per protein, or per gram of emulsified per gram of protein, emulsification activity, and then stability. We looked at WPI, which is our reference, the standard. So it's a 90% protein, so it's obviously a better functionality because it's more concentrated in protein. Delactosed whey that is not modified, and then whey protein concentrate, which is a low protein ingredient as well. We used it as another reference. And then what we did is, after doing the RSM, we got conditions optimized for emulsification capacity, for example, or conditions optimized for emulsification activity. When we looked at the conditions that gave us the highest emulsification capacity, look at, with these conditions, we have really minimal degree of hydrolysis, but we were able to establish similar emulsification capacity to a product that has 90% protein. So we went from this much, 1,300 to 1,700, with a product that was less protein. So this is really huge. And we also did look at the one that was optimized for higher emulsification activity. But again, it had really good emulsification capacity, not statistically different. Notice the statistics was done correctly here. So this is not statistically different. But again, look at the emulsification stability. We even enhanced it so much that it's higher than WP. And then what my student did at the time, I really need to publish this work. This has been done a few years ago. Still did not publish his work because I didn't have time. But he also produced beef patties and looked at, because in beef patties, you want emulsification as well, because you want to hold on to your oil as well as hold on to the water. And if you hold on to the oil and water when you make that patty, it will have a better texture. And then the highest the compression force, that means the better the texture of the beef patty. It won't crumble fast. So we look at the WPI, it really has the highest value, and the one hydrolyzed as well, D-lactose whey alkylase, has very similar to WPI. However, DLW alone also has less force. That means we were able to improve it and make it comparable to WPI by really targeted modification using that RSM design. So that was a successful kind of research to show you that through targeted enzymatic hydrolysis, you can reach a goal, the goal that you want. And you would optimize based on your target. So our target or emulsification capacity, we optimize to that. If your target was solubility, you can optimize to that. Okay, so another experiment we did is just to show you that when you hydrolyze, you don't always get a positive result. So in this case, we were looking to enhance the solubility of soy protein isolate. Well, here we started off with a really good solubility because the soy protein isolate we worked with was native. That means was not subjected to any thermal processing. So we looked at different enzymes to see the impact of hydrolysis on solubility and at the same time see the impact of hydrolysis on bioactivity, because that was our main target. We want to produce bioactive peptide, but we want to maintain solubility or improve it. So we looked at different types of enzymes because each enzyme has different specificity, so it will produce different peptides. In every condition, solubility decreased. Obviously, there is more drastic decrease in depending on the enzyme because it depends where it cut and what type of peptides are generated. But why do you think in all cases we saw a reduction? Look at the given up there. Do you know?
I was going to guess that the heat was exposing hydrophobic.
Yeah, all of them were boiled to inactivate the enzyme. So the boiling, the heat treatment, even though we have peptides now, even though we have higher ion density due to breakdown of the peptide bonds, the heating resulted in aggregation and precipitation or loss in solubility. So this is just to illustrate that you have your peptide, you break it down into peptide by hydrolysate. You have your protein, breaking it down, and then you get aggregation upon heating. It still can happen because you're exposing hydrophobic groups. The hydrophobic interaction can still occur and can still cause aggregation. And oftentimes the aggregation is moisture and heat-induced aggregation. So there's a lot of processing challenges even with hydrolysates. So upon heating, your small peptides are still going to aggregate and form larger polymers, and these polymers may not be soluble. And also, instead of just reacting with just peptides, you can have if you have a reducing sugar in the system, it can react with carbohydrates. So you can have hydrophobic interactions followed by disulfide linkages, or you can have polymerization due to Maillard reaction. Polymerization is a consequence of the end reaction or the advanced stage of the Maillard reaction. So when we have this when we have those peptides aggregating, we are going to lose bioactivity of the peptides. You generate peptides for their bioactivity to be absorbed directly and have physiological benefits. But when we heat in the presence of moisture, these are going to aggregate and then they won't be biologically available anymore, and then we will lose their bioactivity. So there are different factors, as we learned throughout the class, that will contribute to aggregation. So intrinsic factors, so that means the percent hydrophobicity of the protein, the amount of disulfide or the sulfide groups that can lead to disulfide interaction. So it's really intrinsic factor of the actual protein or peptide generated. So what kind of peptides are we generating? Hydrophilic peptides or hydrophobic peptides? It really depends on where the enzyme cut. Oh, it was doing that on its own? Huh. Not me, a student of mine did that. Okay, so thermal denaturation, obviously when the protein is denatured, and also when the protein, even if it's peptides already denatured, but when you heat, we have more thermodynamics, so you have more interactions that would lead to denaturation. Extrinsic factors is basically your pH, your ionic strength. So these different, what pH you are of your system, what is the ionic strength of the system, that would also contribute to aggregation. Hydrolysis, if you, depending on the protein and the enzyme you use, you could generate peptides that we call aggregate promoters, because they could be hydrophobic and they could have certain reactive groups that would lead to protein-protein interaction. And finally, the Maillard reaction, which is when it advances to advanced stages, you end up with protein being polymerized. And that is another aggregation. So this, if we want to link this to industry, this kind of moisture-induced protein peptide aggregation affects a lot of different sectors. The baby formula, the nutrition bar because of hardening, protein hardening, and also the beverages because you don't have high shelf life due to protein falling out of the solution in the beverage. So that is kind of the market impact of it. So taking in dry food due to protein aggregate, picking up moisture and causing aggregation over time. So you end up with caking of a product that is a loss there. Hardening of protein bars, which you have semi-moisture product. You still have moisture, so you still get that interaction going on, protein-protein interaction leading to a hardening sensation. And then the turbidity in your beverages and the fallout of solution due to aggregation. So this all leads to reduced shelf life, obviously, of your powder, of your bar, and of your beverage. And thus, this is accompanied by economic loss. So we need to do something, investigate ways to limit aggregation, even of hydrolysates. So even hydrolysates are susceptible to aggregation. So a little bit more about the factors in dry and semi-moist food. So thermal denaturation, we already know that, the denaturation and the exposure of hydrophobic groups and sulfide groups. And then with the, in the dry and semi-food moisture foods, the humidity, where they are stored under, and the temperature. So if they're stored under high humidity, of course, there will be more moisture migration, and the high heat will lead to more movement, thermodynamics again, and formation of aggregates. So that's the caking of powders and the hardening of bars. In a beverage, so the aggregation is obviously through these interactions, for sure, hydrophobic and disulfide. If we have reducing sugars, we can also see Maillard reaction polymerization. This has been proven so much by Ted's work, right?
Yeah.
Yeah. All right, in beverages, different factors, not just beverage, you have moisture, obviously, and you treat to pasteurize your beverage, but other factors that contribute is what's the pH of your system? Is it closer to the isoelectric point? Is it at a pH where you don't have clear protein solution? The nature of the protein itself, is it high surface hydrophobicity, low surface hydrophobicity, ionic strength, and high or versus low protein concentration? The higher the protein concentration, obviously in a solution, the higher tendency to form aggregates during storage. So this is the industry problem, and it has been going on for a while now, is that they want to improve the shelf life of beverages, period, high protein beverages. And they were looking at improving the solubility and thermal stability of whey protein specifically, because it is the golden standard for beverages, but it's still, the shelf life is not very long, so they're still looking at ways to improve the solubility and thermal stability of whey protein. So whey proteins, as we know, is globular in shape. So when you heat, they're going to open up. You've seen this before. Expose hydrophobic groups and cysteine, sulfide groups, so leading to a polymerization and separation over time. Because you're pasteurizing, you are denaturing the protein. Put that on a shelf for a while, it's going to form aggregates. First you'll see turbidity, and then you'll see fall out of solution. So there are two types of beverages in the market, the neutral one and the acidic one. So the neutral one is usually opaque. Your whey protein is not clear in solution, so that usually it's the chocolate kind of beverage, the orange cream kind of drinks. But the acidic beverage is a huge market because the drinks are clear, and this is usually favored. Clear beverages, clear fruity flavored beverages. So in this case, the pH, however, is really low. You have to go to a pH way away from the isoelectric point. So if we are around the isoelectric point, 3.5 to 5.5, if you remember at this pH, your whey protein is an octamer. In this case, because you don't have a lot of charge, so they kind of form octamers, and the octamers potentially lead to creamy appearance. And also around this pH, they are at their maximum buffering capacity. That means you need a lot of acid to add in order to reduce the pH, because proteins are buffered around this range. They are at their maximum buffering capacity. So in order to produce a clear beverage, we need to break these octamers. So we have to reduce the pH even more. So usually beverages are in the range of 2.8 to 3.4. So away from that octamer formation where you have monomers under that acidic conditions. However, in order to reach this pH, and to overcome the buffering capacity, you add a lot of acid. Then the problem is they're sour and they're astringent. So now we have three problems: sour, astringent, and not thermally stable over shelf life. So you short shelf life. So if people have targeted hydrolysis. Okay, yes, we have improved solubility, we have improved thermal stability, yet in order to get significant improvement in solubility, they found that you really need to hydrolyze a little more than the perception of bitterness. And that caused a potential problem. And then hydrolysates are better buffers because you are now breaking the peptide. You have amine and you have carboxyl. You're generating more groups to buffer. That means you need to add more acid to reach the desired pH, then more sourness and astringency. Over time, you are still going to form polymers. So even though they are initially better, more soluble, but over time, these peptides can come together and aggregate and form large aggregate and precipitate. So we're not solving the shelf life problem. So here where Maillard reaction comes into play.
I have a question about the whey protein, but it's related to different functionality as an emulsifier when we open up the protein naturally. So it's losing its globular structure. So will it be able to form the thicker edge layer we discussed the globular protein?
Partial denaturation is always your key. But even when you break it, it's still smaller in molecular weight. Even when you open it up, it's still smaller in molecular weight than casing it. So you can still have more of it on the surface. Yeah, so it's smaller smaller means more of it on the surface. So here's where we come to Maillard reaction. And you don't want really the whole Maillard reaction. So you don't want the initial, intermediate, and advanced stages. You want the initial stage of the Maillard reaction. So that's why we call it Maillard-induced glycation. We just want to form the Amadori compound. And the Amadori compound is your glycated protein. And that's why it's called Maillard-induced. Because your glycated protein is formed via that initial stage of the Maillard reaction. And you already know what the Maillard reaction is. You have an amine group, a reactive amine group, either a terminal amine or the epsilon amine from your lysine is most reactive. It reacts with the carbonyl carbon from a reducing end of a carbohydrate. And then it's a condensation reaction, so you form your first stable compound, which is the Amadori compound, shift based on an Amadori compound. So the Amadori compound is your first stable compound of the Maillard reaction, and then you want to stop it there. You do not want it to progress any further. So you just want to produce your glycated protein. So the sugars or carbohydrate moieties are attached to your protein at certain locations where you have lysine. Mostly it's with lysine. So you know, Maillard reaction, who wants to know what it is? Nobody wants to know what it is. It's a complicated reaction, but what we want is the formation of our shift base into Amadori compound, and that's it. We don't want it to propagate into intermediate. We don't want it to go into advanced AGEs or advanced glycation end products, which can also lead to polymerization, to off flavor, to browning. We don't want that. So basically, again, this is highlighting that we just want to focus on the initial stage where products are colorless, we have a condensation, and we have the first stable product, which is the Amadori compound. We don't want intermediate stage or final stage that are mutagenic, of flavor, excessive browning, polymerization, so you don't want all of that. So when you have polymerization, you have poor protein solubility. Excessive Maillard reaction, you get nutritional loss because you lose lysine. And of course, mutagenic and shorter shelf life because of browning and off flavor and polymerization. We don't want all that. So in order to control it, in order just to achieve the glycation and not go further, we have to control the conditions of glycation. So what we do usually is we control temperature and water activity and the type of saccharide that we use. This is how we control it. So temperature, we choose a temperature that is not very high. First of all, that will obviously higher temperature, higher rate of reaction. We don't want high rate of reaction. So lower temperature, but the temperature that is enough to initiate the reaction, and it's below the denaturation temperature of the protein. We don't want to react at 70 degrees or higher, for example, for whey protein. We want to be lower than that. The optimum water activity for Maillard reactions being 0.5 to 0.7. This is really good for it. So we try to be close, but not in that range, a little bit lower. And what we worked with is 0.49 water activity. Use of polysaccharides, usually maltodextrins and dextrins, so that our smaller sugars will react really fast. Larger, bulkier sugars will have steric hindrance and won't react very fast, so we can control the reaction. Make it slow and able to stop it when we have enough glycation. And we want to target partial glycation. That means that we don't want to take every single lysine and add a sugar moiety to it, then we are losing the nutritional value. So a couple of carbohydrates on the protein should be sufficient to cause what we think is going to happen. And what we think is going to happen is, this is the prediction, when we have a sugar reacting with amine, that means we're blocking a positive charge. That means we have an increased net negative charge. So now we're increasing the load of net negative charge, then we are increasing the repulsion between the proteins. With the sugar on top and more net negative charge, that means we have more hydrophilicity. With more charge and the sugar around its solivation with the water, we have lower denaturation rate. So we have repulsion now, so the protein is not interacting via hydrophobic interactions. Then you will have reduced disulfide interchange because they are far further apart. And the presence of a bulky carbohydrate also causes steric hindrance, also causing it to be further apart, and you have increased solubilization. So this is kind of our hypothesis of what happens. And this is how we do it in the lab. We incubate, we mix them. In this case, we work with whey protein hydrolysate. We mix them with a dextran or maltodextran. We put in an incubator, well, we have an incubator or a desiccator with particular salt to control the water activity. And then we incubate at 60 degrees C. And we pull out samples at different time points to test the amount of Maillard reaction. After we glycate, we want to remove excess. Okay, I didn't do that, and my student did. So what we did is you have free non-reacting carbohydrate, and then you have the reactive carbohydrate. So we want to remove those that did not react. We don't want more sugar in our system. We want to remove them. So what you would do is, I don't know why this animation is slow, but we use hydrophobic interaction chromatography to separate our non-reactive sugars from our protein. And the protein that is glycated is collected with the protein that is not glycated. So if you remember from protein separation, we run with salt first. So our sugars come out in the salt and the protein precipitate on the column. But when we add water, the protein comes out. And then we test total carbohydrate in different fractions to confirm that all the free sugar comes out first and only the glycated sugars remain with our protein fraction. So that is maltodextrin alone. Most of our maltodextrin come out first. The unincubated, only mixed together, also they come out first. And then the incubated, when we have the dextrin and the protein, we have a little bit of carbs here with the protein because this is the glycated protein. So we confirm the separation that way. We measure Amadori compound by measuring absorption at 304, so at different incubation times. With the control and the sample, we look at increase in Amadori compound to know where we want to stop. It seems here would be a good starting point because we don't see much increase after that. So the shorter amount of time, the better. We looked at browning because we don't want Maillard reaction to increase. And we looked at intermediate products by looking at fluorescence. We want to make sure that our sample is not progressing into intermediate reaction. We want to make sure that we stop it where we do have Maillard induced glycation but no intermediate product. We measure the percent loss in free amine. If you remember, we talked about that. So you measure the total amine, free amine first. After incubation, you measure the loss. That gives you an indication of how many free amines reacted. So again, somewhere between 60 to 72, we have about 24% of our amines reactive or free amines reactive. So that is good. We have good reaction, but it's still partial, not all of them. And then, not going to dwell too much. This is just to link structure to function. I think I showed you some of this before, looking at the solubility at different pHs. It reached above 90% or higher, even around the isoelectric point. So we can make a beverage, instead of being 3.4, we can make it 4.5. It's still acidic, and it's still going to be clear, and solubility is good, and it's not going to be sour, it's not going to be astringent. We did sensory tests to prove that as well. We did beverage sensory tests, and it worked out really well. So I think you saw this before. The denaturation temperature shifted. No polymerization was observed after heating over extended period of time. This is the non-glycated, this is the glycated, and then the surface hydrophobicity increases for the regular protein, decreases due to polymerization, whereas the glycated protein, you have slight increase and it plateaus. So we relate the structure to function. I'm going to skip that because I showed this to you before. With ramen, we also looked at changes in structure, and when glycation, we had rigidity in the structure. So you've seen that curve before. So with glycation or glycoconjugates or glycoproteins, you can not only just improve solubility, but depending on the conditions of glycation, you can have enhanced emulsification and foaming, stronger gel, also antioxidant activity, antimicrobial, anti-carcinogenic, so a lot of that. I'm not going to explain this, but you can do biotechnology. I have a few slides on that, but I'm going to stop very soon here. I just want you to know there's a difference between breeding and genetic engineering. Breeding, selective breeding, is you just combine different lines together, you breed them, and you get a new population. Whereas with genetic engineering, you insert a new DNA, and with insertion of a new DNA, you change the protein structure. You can cause a change in the protein structure. You can reduce allergenicity that way. You can change the binding sites of enzymes, so you can change the sequence, so you change the plasmin in milk, for example, no longer can break beta-casein over storage. If you genetically modify the beta-casein sequence so that it won't recognize, or lysine won't recognize, plasmin won't recognize it. You can induce secondary and tertiary structural changes to enhance the functionality. So you can really do that. And this power of genetics, you know what that is? What is that? A cat? It's a puppy with genetic modification. So they inserted a gene of mutation, and this is the mama puppy, Pama, and these are the puppies, and this was one of the pups. You can look it up, you can take that picture and insert it in Google, and you can read the article about it. So you can, basically you can do anything with engineering, but yeah. You can look through the slides later for FYI, but here's where I'm going to stop. Before, don't go. You're going to fill evaluation. So Lucy is going to hand them out as soon as I walk out. I'll try to walk out as fast as I can.